Before we go on with more equations, let's stop and appreciate how beautiful classic mean variance portfolio theory is. I started with the diagram version, which shows the classic mean variance frontier, which we talked about earlier. Now we're ready to talk about who holds portfolios on the mean variance frontier. Our equation was W is 1 over gamma times a mean variance efficient portfolio. In graphical terms, the mean variance efficient portfolio, we start with the original returns. We minimize variance for given mean. That forms the mean variance frontier. I've drawn in the case where there is a risk-free asset as well. So there's a common portfolio of risky assets there, and then consumers with different risk aversions, investors with different risk aversions, choose here's a risk-averse investor, there's a less risk-averse investor. They're just scaling the same portfolio. This is a set of portfolio weights. They're scaling them up or down by the amount gamma, mixing them with the risk-free rate. That's the famous two-fund theorem. Every investor, we don't all hold the same thing, but we hold the same composition of risky assets. We just some lever up more, some lever up less. The composition of the optimal risky asset portfolio is the same for everybody. This was thunderous news when it first came out, because everybody took for granted that you form your portfolios by getting some professional manager who picks the portfolio that's right for you. Just like all the ads said, we listen to what you want, we get your portfolio. Nope, that is completely pointless. You don't need tailored portfolios, you don't need management. You just need a very widely diversified mean variance efficient portfolio. Another thing this tells us, why was this so important when it came about in the 1960s? Only means, betas, and sigmas matter for portfolios, means and covariances. It doesn't matter what the style is, what the name is. Do you need alternative investments? Do you need domestic equity? Do you need fixed income? Do you need exposure to foreign? Do you need whatsoever? Nope, none of that matters. What matters is means, betas, and covariance matrices. The other thing it's very useful to remind you, you think about the portfolio, not assets in isolation. Do you want to buy some venture capital? I don't know. Depends on what else you have. You think about the portfolio. Assets are only there to contribute to a portfolio. These fundamental principles are true in the most complicated portfolio theory we'll write down, and they are almost completely ignored in practice, which is an important thing to remember. Portfolio theory is perhaps not so useful for giving you precise quantitative guidance as what to buy, but it certainly is useful for keeping you from making stupid mistakes. I like to express portfolios relative to the market, so let's do the same thing with this mean variance efficient theory. Suppose that's the if there, suppose everybody else is like this and solving the same kind of portfolio problem. It's just people have different risk aversion coefficients. Well, then the weights that you put in are related to the weights of the average person, the market weights, by your risk aversion versus average risk aversion. Your portfolio is the risk-free rate plus the ratio of your risk aversion to average risk aversion times the market portfolio. By saying everyone is like this, what we have done is we've identified that thing there with the market average portfolio. That's, I think, very useful, because I find it hard to think about what's sigma, what's mu. I don't know my risk aversion coefficient, but I have some sense of whether I'm more or less risk averse than everybody else. And if I think everybody else is solving roughly the same problem as I am, then I don't have to compute sigma inverse mu. I just have to buy more or less of the market index and sleep happily at night. If everybody is like this, of course, we've proven, then the market's mean variance efficient, then the CAPM holds. So the fact that the CAPM doesn't hold might be some clue for us that we need a more interesting portfolio theory for individuals, or at least for the average individual. Another useful rewriting of the same problem, in a way that we almost always rewrite it. Alphas. People don't like, why do people not like this advice? Because they think things are underpriced, things are overpriced. They know how to get the high alpha securities. Okay, when you're doing that, or when you're working for somebody who thinks they know how to do that, it's useful to write the statistical model in this form. So let's write the statistical model in terms of alpha, beta times the market, or any factor index that you like. This doesn't have to be the market portfolio. We don't have to have the CAPM. Any factor model works the same way. And then let's ask the question, our portfolio, how much should we put into the market index, or whatever index we're using here, plus how much should we put into the original returns hedged out of their market beta. In other words, state the question as how much do you put in the market and how much do you put in alpha opportunities and their residual risks. And I denoted these to remind you these are vectors. So there's a vector of alphas, a vector of residual risks. That is a vector of portfolio weights. If we restate the problem like that and resolve it, the answer comes out in a very intuitive way. First of all, the market weight is 1 over gamma, mean return over variance of return. That's exactly the same formula we had before, just with the market return. Then how much do you put into each of the alpha opportunities? 1 over weight, covariance matrix of the residuals, and that's how much you put in the alpha. So this separates the decision. There's one group that can think about factor risks. How much do we want to put in the market? How much in HML? How much in HMB, SMB, and so forth? A completely separate decision is to what extent do you want to chase different alphas. And there, you do it by diversifying across the various opportunities. You look at the covariance matrix. You don't necessarily invest in the high alpha opportunities. It depends on the covariance matrix of the various opportunities. You might, in fact, put a positive weight in a negative alpha opportunity if that thing hedges out some of the other positive alpha opportunities. You may put a large weight in things with very small alphas if those things have very small residual risks as well. So the two decisions are factor risks and then optimally taking advantage of whatever alphas you think you have. Those can now be separated just by writing the problem this way. Let's look at the numbers. Does this advice make any sense whatsoever? Well, one number, let's look at 1 over gamma, mean over variance. Does that come out, anything vaguely reasonable? Mean return of about 8%. I put in a variance of 20%. Standard deviation of 20 squared, that gives a variance of 0.04. With a risk aversion of 2, that says put your money in the market. So this comes out, the ballpark numbers come out very reasonable. That's kind of nice. On the less nice side, the advice hold consumption proportional to wealth says that the variance of your consumption should be the same as the variance of your wealth. Variance of stock returns is 20% per year. Your consumption should be varying by 20% per year. Nobody's consumption varies by 20% per year. If you don't feel like taking that advice, and you do like taking that advice, something's wrong with the model, and we got to fix the model so that's more reasonable before you take that advice too seriously. Another sad point of this whole business, sigma inverse mu is very, very unstable. So this isn't terribly good computational advice. Portfolio maximizing problems turn that, which is one line of MATLAB, into a huge thing and not very successfully surmounting the instability. The problem of the instability is take two stocks A and B that are in fact identical but have a small difference of mean in samples. Well, a portfolio optimizer will tell you short B, long A a huge amount, taking advantage of this small but not significant difference in mean returns. That's that will tell you short B, long A, but it's completely garbage advice, and that pervades portfolio maximizers. But so we have some problems, but we know this is wrong. The CAPM is false. The model assumed people don't have jobs. The model assumed that mean returns and variance returns are constant over time, and we know they're not. We need a better portfolio theory, right? We need a portfolio theory that allows consumers to have jobs, that recognizes that moments vary over time, that will produce the CAPM violations of the CAPM if everyone follows that portfolio theory, and hopefully will fix this problem. Let's do a better portfolio theory.